In the first part of Notes 14, we got introduced to an example that we're going to use to try to um, investigate what we can do when we have questions related to the relationship between two qualitative variables. So there's two ways that we can set up the hypotheses for tests like this. Either one's perfectly fine, they mean the same thing, but you may have a preference for one or the other. So the first version, without getting into specific variables, our null model, so again, nothing is going on, says that the two variables are independent. Another way of thinking about this is to say that the two variables are not related. If I know something about someone's age range, that tells me nothing about how they'll feel, whether they'll feel overloaded by the amount of information or not. So that's the nothing is going on version. And then the alternative hypothesis, well, if our null said that the two variables are independent, we might say that our alternative is the two variables are dependent. Or I actually sometimes prefer to just say they're not independent, so that I don't have to worry about dependent making it seem like there's some sort of causal relationship between them. But either one is going to be fine. All right. So that's general version 1. Two variables are independent for the null. Two variables are dependent or not independent for the alternative. And if we had started for our null by saying the two variables are not related, the alternative would just say there's some sort of relationship between the two variables. Now, what that relationship is, who knows? It could be any number of things. But there's something going on between these two variables. Think of this one kind of like when we say mu1 minus mu2 equals 0 for the null, versus mu1 minus mu2 is not 0 for the alternative. In that case, we would be saying, who knows what the difference is between these population means? It's just not 0. All right. So one thing I want to note is that when we write this out for a specific problem, we should make sure to put them in context of our problem. We're not going to write these in symbols like we have for other hypothesis tests. So it's important that we use specifics in the setup so that it's easy for someone to tell what it is that we're actually testing. So if I go back to the example from part 1 of Notes 14, and I wanted to say what my null and alternative hypotheses are for this problem, one possibility is to say whether or not someone feels overloaded by the amount of information available to them, that's my first variable, is not related to their age range. That's my second variable. And notice that the study only looked at 18 to 64-year-old Americans, so I might want to make sure that, any conclusions I make should be restricted to that group. I don't know how 80-year-olds or 5-year-olds feel. All right. If that's the way that I phrase my null hypothesis, then for the alternative, I might say something like, well, there's some sort of relationship between age range and whether or not someone feels overloaded by the amount of information available to them. And again, this is just among 18 to 64-year-old Americans. If I had chosen to do general version number 1 up here, I would have said someone's age range and whether or not they feel overloaded by the amount of information available to them is independent of one another, or age range and whether or not someone feels overloaded is not independent of one another. So that's how we can set up our hypotheses. And if you think about ways that we have approached hypothesis tests in the past, we set up our hypotheses, and then our next step is almost always to calculate a test statistic. So remember from previous sets of notes that a test statistic is a number that's going to summarize our data, but it's going to do that in relation to a null hypothesis. So in our example, our null hypothesis said these two variables are not related to one another. What that means is we need to figure out what would our data have looked like if our two variables were not related. So we don't know one way or another yet what's the case, but we can calculate something that we refer to as expected counts, and those expected counts will tell us what do we expect when the null model is true. That's going to allow us to compare what we actually saw to what we think would happen when the null model is true, and use those to calculate a test statistic. So this will be a little different than other test statistics that we've done, but it's following this same idea. So an expected count, the way that we find that is we take the number of observations we would expect on average if the null model were true. And we can calculate that by taking the number of people or objects in the row for whatever cell in our table we're looking at, multiplying it by the number of people or objects in the column for whatever cell we're looking at, and dividing that by the overall total in our sample. So we can look at our example here that we've been working on to see what we mean by this. And I've got this one highlighted right here. All right, so if I go back to the previous page, there were 35 people who were 18 to 29 and felt overloaded by the amount of information available. We want to know how many people would we expect in this cell if the null model is true? If whether or not someone feels overloaded is not related to their age range. So again, the way that we're going to do that, we'll take the row total. So for this cell, there were 269 people in that row, and there were 210 people in that column. So row total times column total, you can see right here, 269 times 210 divided by the overall total, which is 1151, and I get 49.08. Now, it might be tempting to round that to 49 because I know that I can't have 49.08 people. I could have 49 people though, for example. But recall that I said that these are what we would expect on average. So we don't actually have to get whole numbers, right? I can have an average class size of 29.5. Now that doesn't mean that I actually have half a student, it just means that maybe sometimes I have 30 and sometimes I have 29, all right? So for this example, I'm rounding everything to 2 decimals. And the reason that I'm not rounding even further is we're going to take these numbers and we're going to compare them to what we actually saw, and then we're going to do some other stuff with them to get our test statistic. And if we round too much early on, it can really throw off our answers later, all right? So you might want to try this for a couple other ones of these. Don't look at the calculations yet. See if you could verify these numbers doing this on your own. There's also an activity where you'll be able to practice this later. So how do we use these expected counts? Well, I said that we want to compare what we actually saw, so our data, to what the null model says. And we've got 6 different cells in our table, and we're going to have to do this for each of those cells. So the first thing we'll do is we'll just take what we observed minus what we expect when the null model's true. We're going to do that 6 times, all right? Once for each cell. So if we had a bigger table, we might actually do it more than 6 times, and so on. And that's going to tell us how far away the thing we observed was from what we expected. Then we're going to square all of those differences. And the reason is otherwise we get positive numbers, negative numbers. We don't want them to end up canceling out and stuff like that. So this is just our sort of mathematical way to get around that. And then we're also going to divide that squared difference by the expected count. And the reason for this is that this accounts for the fact that if we looked at 1,000 people versus 20 people, well, it probably wouldn't be that weird to see, 10 more people in one group if there's 1,000 people in the sample than if there were only 20 people. And so it's kind of standardizing things. And then lastly, we're just going to add all of these numbers together. So this is sort of a lot to follow, but we'll look at an example here real quick. So again, take the observed value minus the expected for each cell, square that, divide by the expected, add all of those up, that's all this symbol means, and that will give us what we're going to call our chi-squared test statistic. So if I look at the example that we've been working on, you can see that for the top left cell, so that was the 18 to I think 29 or something like that year-olds, and those that felt overloaded, there were 35 people in that cell. If the null model was true, we expected 49.08, so that's our difference. We're squaring that difference, we're dividing by what we expected, and then we're doing it for every other cell in our table. All right, so 6 cells total. I tried to use colors so you can go back and forth and see how these compare to the expected counts that we calculated before. And you can see that if I just do this part here, I get something that's a little bit bigger than 4. If I do this part here, I get something that's a little less than 1. And I'm basically just going to add all of these up and I'll get what I'm calling my chi-squared test statistic of 13.872. All right, so what I want you to think about before you watch the next portion of this video is if the null model is true, do you think I would get a large number or a small number for my test statistic? And conversely, if the alternative model is true, do you think I would get a large number or a small number? And try to figure out which it would be, and maybe come up with an explanation for why that's the case. And it might help to look back through how we calculated this. What do we mean when we say expected? Are we referring to, what we expect in a certain situation? And at the beginning of part 3 of Notes 14, I'll talk through how we can decide, what kind of test statistics we would get in different situations and how that might actually help us calculate p-values and reach our conclusions at the end.